His zero-shot learning work was featured at the United Nations, and his creative AI work was featured in MIT Tech Review, New Scientist magazine, Forbes Science, and HBO's Silicon Valley. And now let's open our ears and minds to Mohamed Elhoseiny. Welcome, Mohamed.
Thanks a lot, Christoph, for a nice introduction. I'm excited to be here to share with you a little bit about my journey and my excitement about this area of creative AI. And today I'm gonna cover psychology of human creativity and emotion. I have actually guided already some of the recent AI developments. And if we extend our imagination for that, actually AI, like psychology, has helped AI to do quite a lot of things that are useful. It helps us to see, create, drive, and feel by explicitly modeling imagination, which is a key element of human intelligence. I'm gonna go through like on that during the talk. And before I start, I'd like to thank a lot of people who have been part of the works that I'm going to go through today. Some of them actually are helping present the workshop that will happen right after the talk. So how explicitly modeling imagination? You can think about imagination as some math that we can use to teach machines to create novel stuff, or also to understand the world around us. To give you an idea about how this whole thing started, and like, as Christoph mentioned in the introduction, I work in what people call zero-shot learning. But what zero-shot learning is, it's a task of understanding object and like an object that in our physical world, a visual object, based on a description that we have never seen before. So for example, if I describe this bird, Parkirokut is a small bird that have an orange beak, and the plumage of the bird is dark above and white below. Maybe that bird name might not be familiar for many of us, but if I describe that in language, it will be easy to recognize that this is the bird we're talking about, right? So that basically this ability that human has can actually help us imagine. Why do we have this ability? Because we can, from that language description, imagine how this bird may look like, and basically from that imagination, we can recognize that bird even if we didn't see it before. So we use our imagination element of intelligence to understand and to extend our understanding of the world around us. Right? And the surprising thing is that that one of the key, I would say, approaches to do this, and it does this really well, is based on imagination. So what I mean by that is that we have a model like a neural network that takes that language description of the bird that we didn't see before, and it tries to imagine it explicitly in the visual world, which is depicted in the picture on the right. So for every bird that you have not seen before, you have an explicit machine learning component that tries to model its imagination, so that when you get exposed to a picture of it later, you can really understand it. And that way of modeling it helped it improve our ability to understand the visual worlds. In this case, I like so much birds. So I work on a data set of birds, and we try to test the ability of the model to extend our understanding of birds to unseen species based on only a language description similar to the one that we just went through, right? So how does this relate to art and fashion? In fact, they are related, because both art and fashion are still based on imagination. Here is another word, I'm using it alternatively with the word generator, right? But I'm trying to, what I mean by imagination here is explicit, is a specific kind of generation that encourages the model to go beyond what it has seen already, tries to create beyond it. And in the context of fashion, how do we extend our imagination? For seeing, I want to extend my imagination so that I can understand unfamiliar birds or unseen birds. in art and fashion, I want to extend the imagination of a machine learning model to produce novel art. And we still designing, we are a part of the process. We engineer how it does this imagination. So we are engineering, we are still the people who are creating or guiding this art, but it's just an additional hammer we use to assist us to create art or fashion. So in the case, I think yesterday, I was also part of the Creative Adversarial Networks. Professor Gamal described Kant, and let me summarize it quickly. It's you're having, let's say, access to some of these visual art styles, like Renaissance abstract art, cubism, and you want to extend the imagination of your AI model to produce patterns that it hasn't seen before. And the idea is based on the principle of least effort, where the x-axis is novelty and y-axis is likability, often also referred to as hedonic value. And as novelty increases, people, like when the novelty is small, you can see that the people may not like the work, but as novelty increases, people will start to like the work more and more, but not for too long. After some point, when the work is too novel to understand, such lack of understanding is pushing off the limits. So people may not really appreciate what's going on because they don't really relate or connect to it or understand it, right? And that's called the principle of least effort. And the key idea is, how do we better model this novelty so that it lives in this sweet spot that we want it to be? And that can help us do a lot of things. So for art, if we do the we picked our favorite GAN model, it may generate the Mona Lisa again, but this is not a novel content anymore. We, in order to alleviate this issue, we added a loss function, and this loss function encourages the generated image to be different, to be hard to classify to any of the existing art style that we just talked about here, like abstract art, cubism. So we want to generate an image, let's say here, I want to generate this image such that it is not, it's not abstract art, it is not cubism, it is not impressionist, it is not high Renaissance. So, and we will formulate that by this loss function. But the nice thing, or the fun part that is nice to exercise here, is that this loss function is, there are the possibilities to change this loss function is countless. Like we tried this formula, which is basically encouraged to be explicitly hard to classify, but later we saw people come up with different loss functions, and you can also do that. Like you can try another formula that you think is better for your application, whether that be art, fashion, designs, and things like that. And that what fascinates me, that this extended ability that we can give to machine as a tool can help us create a lot of things and accelerate creation of creative industries, and provide creative individuals with tools that that can make them do new things. All right. So, and this loss function relates to this the principle of least effort, because we are trying to encourage whatever the model, whatever art the model comes up with, to be hard to classify to any of those existing classes like cubism, high Renaissance, etc. But at the same time, we are not encouraging it not to belong to all of them, or encouraging them to be more like a combination of these styles, like something between them. And this encourages the novelty a little bit. So, I like it. So this encourages the novelty, improves the novelty. But since we're still encouraging it to be more like a combination of existing styles, it doesn't push it off the limit so that it's still contained in this desirable region. And as I mentioned, this is just one way to model this deviation from existing style, but the approaches to that is an open problem, and it's open to creativity of people who are using these tools, right? I like it. So this is really cool. This is so just, who painted it? A machine.
It's actually the first work of art made by AI to be sold at Sotheby's. Sorry, I'm late.
So this is just a scene from HPO that shows the coverage of our artwork back in 2017, and these are some generations that you can see. Most of them are abstract, extending existing artwork. And one thing I want to share also today is that this idea of creating new visual or new visual patterns is not restricted only to art. It can extend also to fashion, and we tried that. And that's the ECCV PIS paper we received back in 2018, and it was about the applying almost very similar loss function, but for fashion, and that encouraged the model to create these pants with extended arm sleeves. So this is an existing shape in the data set. The model only have seen t-shirts and pants, and it learns somehow to come up with a new shape. And if you look at other examples, it's kind of the same. So this kind of way of thinking or way of modeling generation seems to be helpful, and we're working also with some like professional designers that helped us to evaluate this kind of thing, and they found this can provide inspiring examples for designers to help to create new fashion designs that relates to the company's DNA, and you can actually control this a little bit. One thing I want to say also that it's this way of modeling in terms of machine learning perspective, this way is extending not only creative, it's anything that we want to encourage the machine learning model to learn that goes beyond what has seen, right? So we talked about this fashion and art. One thing that we learned from this, one interesting thing is that creativity, right? So this one, that curve of creativity is coming from psychology, right? It's coming from Martin, that who's a Canadian psychologist, right? And that inspired us to produce models that can create novel art, like Can,
I like it.
create novel fashion, like creative fashion networks. But also it helps us to create models that can see things that in a better way. So in this case, modeling deviation from an unseen bird like crested auklet against parakeet auklet in a way that make the model capable of distinguishing them from one another. They are both very similar. One of them I have many pictures for, and I might be asked to recognize that this is a bird that even if I saw what I saw exactly is crested auklet, the model might be more biased towards recognizing things that it has seen compared to those that we haven't seen. And we need to find a balance so that we don't collapse on recognizing everything as a seen class versus having a model that can distinguish between those two. But we don't want similarly the deviation to be too much so that it disabled transfer from seen to an unseen class. So because we understood that this is an orange beak from parakeet auklet, so you want to understand that for an unseen class as well. We understand the plumage, like the shape of the plumage and the colors of it, also from some seen classes. So you want to still transfer knowledge from that we have learned about birds in seen classes to unseen classes while maintaining while distinguishing between these two categories, which are really different. And if you add this canned loss, creative analytical loss, to a task of recognizing between a seen bird and a very similar unseen bird, like these two, you'll find that the accuracy actually doubles from like 13 to 27 area under the curve, which is a metric used to evaluate this kind of task. So you can see that this shows that the psychology of human creativity have guided us to create novel art to understand unseen birds better. So it's kind of a nice, I find it fascinating actually that we can leverage some of this like scientific some of this science that has been developed in the past centuries to develop better AI model that can do useful stuff. Another thing I want to show you that a lot of us care about, I think our talk about self-driving cars is a sensitive topic, and it relates to safety. And one thing I want to show that we applied the same model, or something is very similar. It requires some adaptation, but a very similar idea to help self-driving cars to imagine or to create driving scenarios that has not been seen before, so that self-driving cars can be more safe. It still uses this hard to classify entropy over seen driving scenarios, and this improves the ability of the self-driving cars to avoid road boundaries in a much more accurate way. So it reduced the error from 19% for the baseline versus 9%. And the prediction of the trajectory of the car in the future got reduced from 6.7% to 4.9%. This is more than 27% reduction. I'm just trying to show that psychology of human creativity, and more specifically this Colin Martindale's amazing curve, has guided us to do very useful tasks. Help us to recognize birds that we have not seen before, and maybe if we have tens of thousands of birds around the planet, and we recognize those that are least seen and report them to people, to decision makers, maybe they can take actions to help this species and that could be in danger and need some actions or something like that. It can help us to create art, music, and can also improve self-driving cars so that one day can be more reliable and more safe. All right, that's basically the idea. I want to talk more about art, and we have proposed recently an exciting data set. It's a collaboration between Stanford, Polytechnique, and KAUST. The CFX executed by a student from Stanford, a student from KAUST, and this was mainly executed while I was visiting Stanford. The idea is actually, some part of it is also connected to psychology of emotions. One of the key inspiring books for us was Lisa Barrett's book on how emotions are made. And it has this nice picture and asked people, do you feel anything about this bunch of pictures? And maybe nobody felt anything, but if you get back the color of that image, now you see it's a snake and it can cause a harm, and then this might construct an emotion like fear, right? So our recognition or understanding of the visual object of our emotional response towards the image is also connected to our perceptions towards it, right? And that inspired us to study this a little bit further. And we propose a data set called Artemis, Effective Language for Visual Art. This paper, we presented it at CVPR, Computer Vision Pattern Recognition Conference, which is the top computer science journal, last June. And it has more than 455,000 language utterances collected on the WikiArt dataset, which is composed of 80,000 images, right? And the key difference between this and the others are basically the emotional component. So existing dataset like COCO, this is a very seminal work, and it have made a huge impact. But it's an objective. Like, let's say both the top row and bottom row talk about birds, but look at the difference. The bottom row talks about the bird. Say a bird is sitting on the table drinking a cup of tea. A small bird sits on the top of a book page. Small birds walking on the grass next to the body of water, etc. So that's describe objectively what's happening in the image, but it doesn't have any emotional aspect. In Artemis, we have something like this painting makes its own paintings, because paintings are more likely to construct emotional responses. This makes me feel like birds are flying on top of my head. This is a picture of a bird that gives me hope. The picture, the pale color palette of the water painting is very relaxing, and I can imagine myself sitting by the water listening to the birds. So it kind of you can see significant increase in emotional aspect when you describe a painting versus in the new data set versus the previous one, and they are of a similar scale. So this 455,000 appearances is of a similar scale to Coco Captions data set. And the reason why we have this response is that we got inspired by psychology of emotions to design the actual interface where we
wissen, welchem Niveau da die Vorträge sind, wo ich morgen hin muss.
So we ask people to select an emotion, like the positive emotions are on the left and negative emotions are on the right, and we give the actual emoji for that so that it helps people to self-recognize the emotion, because Lisa said that when you have an actual face that stereotypes this emotion and people are familiar with, the task of self-recognizing what they feel about this painting becomes easier, because it will become more like, do I feel more like this emoji, right? That I fully recognize what it means. And then after they select the emotion, the language description that we collect from them is an explanation why they pick that particular emotion. And then we have this histogram of the emotions. So these are the histogram distribution of different emotions that we collected from people from the 455,000 appearances. And you can see that I think it's more that the case that we have more positive emotion than negative ones. Like you have more amusement, contentment, excitement than anger, disgust, fear, etc. So the people are more like positive about the paintings and being negative. There could be a little bit of bias. So, and these are some preliminary results that we showed in the paper, and you can see the model have an ability to describe, let's say, starry night painting by like Banco, that by the blue and white. It's the feeling that was produced by, in this case, the blue and white. The colors of this painting makes me feel like I'm at a dream. So these are automatically generated captions given that particular painting. So this shows that actually we can also build emotions that have a sense of describing emotional aspects of it, and we can build, I would say, like some of this to help, I would say, and interact with, let's say, blind people, so that they may appreciate art more. And then I would say, like more recently, we developed a better method that can kind of model imagination or creation of new art as a walking loss. So mathematically, we build. You can think about it intuitively as a random walk loss, and this random walk loss is trying to start from set of scene, let's say art styles. Let's say C1, C2, and C3 are scene art styles, and we want to walk through the gray dots so that we don't land any close to any of the scene classes that we start from. So this is a different way from modeling. As I mentioned earlier, there is scan. We talked about this as a loss function, but another loss function is to model this deviation or model this creativity against art that has been seen by something like imaginative works, which is something we proposed recently. And that loss interestingly improved performance on recognizing unseen birds, but also creating, more interestingly, it produces novel arts. And you can see the difference between, let's say, CAN results in 2017 and the imaginative work results, which are built on top of more recent architecture. You can see that the model is capable of producing more interesting stuff, and the quality of the models are better, and they are also different. So this picture, these are for these two rows, the top part, this 4x4 grid, are all generations of the model, and these two rows shows one of these images and the nearest neighbor paintings in the data set. So this shows that the model created something new, because there is nothing similar to that painting in the existing data set. So So it has some elements of creativity. And the thing here also that people have emotional reactions towards machine generated art. So on that, only 9% of people don't feel anything about this, but the remaining have diverse emotions, and we can describe some machine generated paintings like this by scar, dark, fear, ghost, etc. And these are just machine generated. Some others are excitement, red, interesting, peace, awe, white, interesting, mountain, trees. So people can also, it goes actually back from being mainly abstract in Kansas to later being also describing, also generating paintings that describe objects. And these are some comparison that shows that the new model is better than style GAN plus GAN, which is a 4-year-old model now, and it has this sweet balance thing. It generates images that are that are novel, but at the same time are likable. This is novelty, and this is likability. I want to also share the work that was created by like us and DJ and Hannah. Was like our currently GJ is currently an intern. Hannah was also an intern and at KAUST, and started as the head of Stanford Center of Design and Innovation in South Korea. And we created some art works. This one got accepted at the New York Creativity Workshop 2020. And the nice thing is that recently one of these paintings, which is this one, was featured on the New York 2021 as on the cover page. So we're happy for that. A last thing that I want to share is that we also studied Wolfram principle. I think Professor Gamal talked about it last time, and they have these principles, and it has a really nice. We have a very nice paper on this space called The Shape of Art History on the Eyes of a Machine. We extended this a little bit further to analyze this on machine generated art, and collected Wolfram principle on more than 1,000 paintings. And what we wanted to study that is different from existing work is that we tried to understand how this Wolfram principles of art history. I would refer you to Professor Gamal talk, who talked in depth about these principles. But we tried to discover if there are correlations between these Wolfram principles and emotion. And we found, for example, strong correlation between contentment and planar versus recessional dimension of Wolfram. We found also strong correlation between amusement and absolute versus relative clarity. So this was some of the interesting finding. And this paper actually got accepted recently in the International Conference on Competition Creativity. And with that, I want to thank you very much. And then I would be happy to take a question if there's a room for that. And after that, we'll hand over to the rest of the team to cover like an interesting tutorial on style transfer, style can, music can, emo style GAN, and textual art. And thank you for that.